So welcome to this video on calculating the latent heat of fusion. So the latent heat of fusion is the amount of energy required to change water from a solid state as ice into a liquid state, liquid water. And so with the latent heat of fusion, we're actually looking at no temperature change, just simply a phase change. And so the extra energy that's required for that phase change is going into breaking the bonds in the water molecules between them and other water molecules. So just very quickly, looking at the aim, our aim today is to calculate the latent heat of fusion of water using household equipment. And so if we look at the materials, the household equipment is our electric kettle, our stopwatch or timer, which could be your phone, 250 milliliters of ice cubes. I recommend making these in an ice cube tray, a thermometer, 500 mils of tap water, and a calculator. So our method for this was to measure the temperature of the 500 mils of water. This is our starting temp. Add the 250 milliliters of ice to the kettle. Then add your 500 mils of water, so you'll get a total volume of 750 mils. Then you'll need to turn the kettle on and start your timer. Once the kettle boils, you'll then need to turn the timer off as soon as it clicks, and then record the final temperature of the water. So I guess the most complicated part of this prac is understanding what's going on down here. And so what we can look at is, if we look at these energy changes, we have the energy of the ice melting, so the change in energy of the ice melting, plus the energy of the ice water, so once it's turned into water, it boiling, plus our energy of the actual 500 mils of water that we put in. All of that energy combined will be equal to the amount of energy that the kettle has consumed, which will be W. Now what we can do is we can rearrange this equation, and I might just change that highlighter color there just so it's a bit easier. To follow. So we can rearrange this equation. We're going to hold that on the left-hand side, the energy of the ice melting. And if we throw these two terms on the right, we actually get, well, that's actually equal to the amount of energy that the kettle used, W, minus the change in energy of the ice water boiling, plus the change in energy of the tap water boiling. So that's quite interesting. However, we've got a bit of a problem here. The change in energy of the ice melting, that's not going to really help us, because tied to that delta Q is the mass of the ice. So what we need to do is we need to expand this equation. And so if we look here, this line here is the same as this line here. So delta Q of the ice melting, that is equal to the mass of the ice times the latent heat of fusion. The change in energy of the ice water boiling is equal to, it looks like mice, it's the mass of the ice multiplied by the specific heat capacity of water, multiplied by the change in temperature of the ice water. And then over here we have this delta Q of the water boiling this is the 500 mils of water boiling that we put in there, and it was recorded to be 22 degrees Celsius. Now, instead of us looking at W, we actually need to define W, so the amount of energy the kettle's used, and that's equal to the wattage of the kettle. So we used a 2000 watt kettle, multiplied by whatever time the kettle was on for. So that's why we recorded the time of the water boiling. Just to highlight these, based upon the above equation, we have that plus that plus that equals the energy that the kettle used. Once again, rearranging, we want to make it in the format of this equation, but instead of it being the mass of the ice multiplied by the latent heat of fusion, we're going to hold the latent heat of fusion on the left and move everything else to the right. So it looks very similar to this line, except we've put the mass of the ice down here, so you can see it there. And so that's our final equation. The latent heat of fusion is equal to 2,000 watts multiplied by the time that the kettle was on, minus all these energy changes we've got here. So the mass of the ice multiplied by a specific heat of water, multiplied by the change in temperature of the ice water as it comes to boil from 0 degrees. So that's the water that's formed from the ice melting, plus the mass of the water multiplied by the specific heat capacity of water, and multiplied by the change in temperature of the tap water. So this is the tap water we added, the 500 mils. As we said, that's all over the mass of the ice there. So subbing in some values, this line here is the same as this one here. So you can see there's our mass there, 0.25 kilograms, multiplied by the latent heat of fusion, the thing we're trying to find, is equal to this expression. So the mass would be 0.25, specific heat of water. And obviously that ice water is going to go from 0 degrees all the way up to 99. And then this was the water that we added, the 500 mils that was already at 22 degrees. Because it went from 22 to 99, 21, that's a change in 78 degrees. Once again, the wattage of our kettle was 2,000 watts, and the time it was on for was 180.45 seconds. Just sort of cleaning this up, we get to this next line here. So 0.25 kilograms times the latent heat of fusion is equal to the energy of the ice water boiling plus the energy of the 500 mils boiling is equal to the energy that the kettle used. Rearranging this to make it in the format of this equation here, we have the latent heat of fusion is equal to this term, so that is the total energy the kettle used based upon its wattage and the time it was on for, minus the energy put into the ice to heat the ice water from 0 degrees to 99, and that should be a minus there, we'll just clean that up, minus the amount of energy put into the actual liquid water that we added, the 500 mils there, and taking that to boiling as well. All of that is divided by the mass of the ice to give us the latent heat of fusion. So what's interesting from this experiment is we actually calculated the latent heat of fusion to be 377,700 joules per kilogram. If we put that in scientific notation, we get 3.78 times 10 to the 5 joules per kilogram. This number really has no meaning to us until we compare it to the actual accepted value. So if we scroll over here, the accepted value is 3.34 times 10 to the 5 joules per kilogram. So that's the amount of energy you need to put into 1 kilogram worth of ice to change it from ice to water. Once again, no temperature change is happening. It is simply just a phase change, which is breaking intermolecular bonds between the water molecules. Finally, we can actually look at the percentage error that we have. So how far away was our value from the accepted value? And to do this, we get our value that we obtained and divided by the actual value. So we got 3.78 times 10 to the 5 divided by 3.34 times 10 to the 5. You can actually cancel those powers there and just do this part of the equation. And it ends up being 1.13, which means we're actually 13% over the accepted value, which I'm actually really happy with. The fact that we got a number which was times 10 to the 5 and we're only 13% away from the accepted value is really, really good. Just for your reference, there's a few definitions down here. So if you look down here and you're wondering what's going on up here in this part here, where do all these numbers come from, you can look down here and sort of see where they come from. Okay, so that's actually how you calculate the latent heat of fusion of water going from, once again, a solid, which is ice, to a liquid, which is water, liquid water, using simply just a kettle, a stopwatch, a timer, a thermometer, and a calculator. So well done, guys, and catch you later.